At this point, we have some definitions about graphs under our belts. So now it's time for us to start looking at some more generalized examples of graphs. We're going to look at some special classes of graphs. Now, it is not necessarily, but I do encourage you before watching the video to look at the in-class activities called classes of graphs. That'll give you some of the motivations behind some of the definitions that we're going to have. But in any case, for the video, we're going to first define some important types of graphs, and then we're going to show some visual representations of each one. So our first type of path is going to be called path graphs, and these are, I guess, in some ways you can think of them as the simplest types of graphs, and as their name implies, they are graphs that look a lot like paths. And if you remember what a path is, it is just a walk where you don't repeat any vertices. And you'll see in the visual representations how they look a lot like ordinary paths. Anyway, here is the formal definition. If little n is a natural number, the path graph on n vertices, and the notation for that is Pn. It's a graph with, well, it has n vertices, and you can call them whatever you want. We're going to call our vertices v1, v2 through vn, just so you can see how many vertices there are. And the edges are, well, the ones that are right next to each other, those are the ones that form the edges. So we have v1, v2, we have v2, v3, v3, v4, all the way up to vn minus 1, vn. And here's what a visual representation looks like. Again, they don't have to be v sub number. We're going to use, well, actually, here's what a general one looks like. You can see v1 is connected to v2, v2 to v3, all the way to vn minus 1 connected to vn. And you can see visually it looks exactly like a path did back in our previous video. And if you want to look at a particular one, here's one with 6 vertices. We're not going to use v for these ones. We're just going to use the letters a through f. And you can see we have 6 vertices here, and each one that's right next to each other has an edge between. So the next type is going to be called cycle graphs, and these are a lot like paths, except they begin and end at the same vertex. They kind of form a cycle particularly, but if you imagine, when we see the visual representation, it's going to look like a little bit like a circle. So once again, let n be a natural number, and we're going to look at the cycle graph on n vertices, and the notation for that is Cn, C for cycle. And that is going to be the graph with, well, we have n vertices, so v1 through vn just shows you how many vertices we have. And the edges are going to look a lot like those for the path graph. In fact, we have all the same edges, v1, v2, v2, v3, all the way up through vn minus 1, vn, except we have now one additional edge between the first vertex, v1, and the last one, vn. That's the vn, v1 at the end there. And that sort of closes it out as a cycle. So if you want to see what that looks like visually, so we start up at the top there with v1, work to the right and down, v2, v3, v4, all the way around, then vn minus 1 to vn, and then there's another edge between vn and v1. And if you want to look at a particular one, here's c4. That one, we have 4 vertices, and again, that one looks like a square, but you know, you can imagine it looks like circular-ish, right? Or at least like a regular polygon. All right, so now we're going to look at a complete graph. So now imagine a complete graph as you have a bunch of vertices, and how can we draw as many edges as we can? Well, here's a formal definition of what that would look like. Again, n is going to be a natural number. The complete graph on n vertices, and that one's going to be called Kn. We want complete. C was already taken for the cycles, remember, so K is the only other thing that sounds like complete. So we're sort of stuck with Kn. And that is going to be the graph, again, with n vertices, which we're calling in this particular portion v1 through vn. And our edges are going to be vi, vj, where I and j can literally be any number between 1 and n, except we don't want them to be the same. So I is not equal to j, and that just says that we want every pair of vertices to have an edge between it, but we don't want edges between a vertex and itself. Right? We're not going to have a reflexive property here. We're not going to have any loops. So it's kind of hard to show what that's going to look like in general because there's just too darn many edges. But I'm going to show you what K5 looks like. So K5 is going to have 5 vertices. And once again, I'm just going to use letters A, B, C, D, E. Or no, actually in this one, I'm sorry, we're using 1, 2, 3, 4, and 5. I don't know what the heck my vertices are anymore. And notice that each pair of vertices has an edge between it. So we drew as many vertices as we could between those vertices, or as many edges as we could between those vertices. So the next one is, it's going to have the word complete in it, just like before. But this is going to be called a complete bipartite graph. And it is very similar to the complete graph in that, in some sense, we're going to draw as many edges as we can between the vertices, except we have one slight restriction. We're going to have 2 teams, and we draw as many edges as we can, but no edges between vertices that are on the same team. All right, so here's how we're going to do it when we define it precisely. So now we're going to let m and n both be natural numbers. So we're going to have 2 natural numbers, each one kind of representing the number of vertices on each team. The complete bipartite graph with parts of m and n vertices is going to be, well, first of all, the notation, we're using the k for complete, just like we did for a regular complete graph. But we're going to put the m and n as subscripts, but with a comma in between, so we know what the size of the teams are. So this is going to be the graph with, well, this is how many vertices, and I'm dividing them into 2 teams. I have the V team, V1 through Vm, and the W team, W1 through Wn. And notice there are m vertices on the V team, n vertices on the W team. There don't have to be the same number of vertices on each team. And the edges are all possible edges between vertices on the V team and vertices on the W team. So that's going to be, if we're writing this in set builder notation, it's going to be all VIWJ, where the I's can be between 1 and m, and the J's can be between 1 and n. And again, it's kind of hard to show you what the complete bipartite graph looks like in general. We'll do a specific example. We'll look at K3, 4. Now remember, the 3 and 4 mean that one of the teams has 3 vertices, the other team has 4 vertices, and the complete part says that we're going to draw all the vertices that we can between vertices on different teams. So you can see the V team on the left, V1, V2, and V3. You can see the W team on the right, W1, W2, W3, and W4 on the right. And notice that we have all the possible edges that we can draw between vertices on the V team and vertices on the W team. However, also notice that there are no vertices between the V team, between V1, V2, and V3. And there are no edges between the vertices on the W team. W1, W2, W3, and W4. But all the other pairs of vertices, we have edges between those. All right, so now that you've seen these examples, go back to, if you need to, go back to the PDF file, classes of graphs included with this video.